Hello, everyone. We're gonna move on to chapter 6 now. I hope you're done with chapter 5 and have finished all the homework problems. Please email if you have any questions on any of the problems from there. Okay? All right, so chapter 6. What are we gonna do here? We're gonna look at multiple random variables at once and we're gonna look at their joint behavior. How do they behave together? So we're gonna start with looking at two random variables at once. And for example, if you're looking at the random variable x and y, we're gonna look at it as a point in R2, x comma y. Okay, the random variable capital X comma the random variable capital Y. And, just it's simplest to think of X as the X coordinate, Y as the Y coordinate. Okay? And we're going to study a lot of things that were similar to what we did in the single variable case, and some things extra do come up over here because of the joint variable, because you're looking at them jointly. Okay? All right. So let's remind ourselves of what we looked at in the single variable case. In the single variable case, we looked at the cumulative distribution function of a random variable. For the discrete case, we looked at the probability mass function of a random variable. And for the continuous case, we looked at the cumulative distribution function, the probability density function of a random variable. And also in both cases, we looked at the relation between the CDF and PMF. That one's easy. You just add up the probabilities to get the CDF. But in the continuous case, that's more involved. What you have is the derivative of the CDF is the probability density function. Okay, so CDF prime is equal to PDF. That's what we had. So these were the main things we looked at in the single variable case. Okay, we're going to look at all of these in the joint variable case, plus we're going to look at some extra stuff. Okay, so starting with 6.1, let's say you have two random variables. So suppose x and y are two random variables. Okay. The joint cumulative distribution function of x and y or some people say the joint cumulative probability distribution function, it's the same thing, of x and y is a function on R2 that is given by, the order matters of course, f of a b. That is the probability of, what do you think? In the single variable case, you had f of a is the probability of x less than or equal to a. Okay, so I'm going to write SVC for single variable case. Okay, and every now and then, whenever appropriate, I'll bring that up. So over here, you have f of a comma b. So as you might have guessed, this is the probability actually read already. Probability x less than or equal to a and y less than or equal to b, or intersect y less than or equal to b. So this is the joint cumulative distribution function. Okay? And let's suppose you can use this to find more general probabilities. Okay? So for example, if you want the probability that x is bigger than a1 less than or equal to a2 intersect y is bigger than b1 less than or equal to b2. How do you find this? Well, it's there's a whole detailed proof given in the book, but I think it's easiest to look at this in terms of pictures. Okay, so first let's just talk about what is f of a b. This is the probability x less than or equal to a, comma, y less than or equal to b. Okay, so let's suppose you draw the line little x equals a on R2 and you draw the line little y equals b on R2. Okay, so this is just, let's suppose you have the R2 and you've drawn the line, actually let me erase that there, and you've drawn the line y equals b, so that that horizontal line is y equals b, and this vertical line is x equals a. What is f of ab? That will be corresponding to this region. What corresponds to this region? That, what I mean to say is, that is the probability. This is the same as the probability that the coordinate pair x comma y, or the point, let's suppose the random variable x turns out to be 3 and the random variable y turns out to be 8, then you would call this 3 comma 8. Okay, so that's just a result. That's just one of the outcomes. Okay, so this is the probability that the point x comma y is in this region, right? Including the boundary. Okay, so just pictorially, I think it helps to look at this picture. Okay, so what if you wanted to look at the probability of x between A1 and A2 including A2, and y between B1 and B2 including B2? Okay, then what will it be? Well, draw the line x equals A1, draw the line x equals A2, draw the line y equals B1, draw the line y equals B2. Okay, and what you want, I'm going to draw it over here, is the probability that the point x comma y is in this set. So I've included the boundary on the top and the right, but not the left and the bottom. You want the probability that x comma y is in this set. Okay, this corresponding to this region. Well, you can just do it like you do inclusion, exclusion. And I'm going to draw 4 pictures. Okay, one of them will be the region to the left of the line x equals A2 and below the line y equals B2. One of them will be this region. So this is f of A2 B2. This is going to be the probability of x comma y being in that region is f of A2 B2. The probability of x comma y being in that region is f of A1 B2. The probability of y being in that region is f of A2 B1. And the probability of y being in that region is f of A1 B1. Okay, so the probabilities of x comma y being in regions below that's what these are given by. And as you can see, what you have is, if you want to find the region of being in exactly just that, you could take f of A2 B2, subtract f of A1 B2, subtract f of A2 B1, but then you would have double subtracted this last region, so you add that back in, okay? So the probability of A1 less than X less than or equal to A2 intersect Y bigger than B1 less than or equal to B2 will be F of A2, B2. Okay, minus F of A1, B2 minus F of A2, B1, but then you've double subtracted the region in this last picture on the bottom right, so you add that in. Actually, let me just put that in this line. Okay, so it's just like inclusion, exclusion that you have seen when you're doing set theory. Okay, so it's just showing you how you can use a CDF to find the probabilities of X being in an interval and Y being in an interval. Okay, all right, so now let's move on to looking at some of the other things we did in the single variable case. That is, we looked at the probability mass function and the probability density function. So let's first do the discrete case of the probability mass function. Okay, so let's look at the joint probability mass function. So suppose that X and Y are two discrete random variables. Okay, the joint probability mass function, I'm just going to shorthand and write joint PMF, is a function on R2 given by little p of x comma y. What do you think that is? In the single variable case, what was it? You have little p of x is the probability capital X equals little x, okay? So in the joint variable case, what do you think this will be? It'll be probability X equals little x and Y equals little y. That's what this is, okay? So that's the joint probability mass function. You talk about this when both the random variables are discrete. Okay, and now let's see. There's something more we need to discuss over here. Of course, for the joint probability mass function, what do you need? You need that P of X comma Y is bigger than or equal to 0 for all X comma Y in R2. Okay, and if you add it up over all the X's and Y's, or if you want to write it as a double sum, that's fine. It doesn't matter which order you add it in. Over all the X's and Y's, you should get 1, just like you did for the single variable case here. The probability mass function is bigger than or equal to 0. If you add it up over all the X's, then you get 1. So over here, you're adding up over all the X's and the Y's, and then you get 1. Okay? And let's now take a look at what the relation might be between the mass function of this random variable X and the joint mass function. So suppose we're looking for the mass function of the random variable X. So that is little p sub capital X of little x. Why am I writing subscript over here? That's because we have more than one variable floating around. We have X and Y as the single cases, so I have to write both of them. Okay, so what is this? This is the probability of X equals little x, right? We know that. So let's now throw in Y. So what is that? That's the same as probability X equals little x and Y is anything, right? We don't care what Y is, okay? So since we know stuff, let's assume that we know stuff about the joint mass function. Let's try and find out what the random variable X's mass function is. So we have that. And what is this? That means we look at P of X comma Yj and add it up over all the different Yj's in the range of Y. All right? Because you want that X needs to be X and Y can be anything. So you have to add up all these different probabilities over all the different values that Y can be. And so you will have the mass function of x. All right. Similarly, if you want the probability mass function of y, that will be you sum up over all the x values, p of xi comma y. Okay, so this is something extra that we have over here, the relation between the individual mass functions and the joint mass functions. It's pretty intuitive, as you would have expected. Okay, all right, so what we'll do next is let's do an example. Okay, and first I'm just going to talk about the example in the book, and then I will mention how we can introduce maybe a small modification to it. Okay, so let's look at example 1a. What do you have? In that example, you have an urn. The urn has 3 red, 4 white, and 5 blue balls. All right, and you're gonna pick 3 from this urn. X will be the number of red balls picked, and Y will be the number of white balls picked. Okay, and what they want is to find the joint probability mass function of X and Y. Oops. All right, so P of I comma J, this is the probability of X equals I and Y equals J. Okay, so before anything, let's take a look at what the range can be. Okay, is it possible that you pick 0 red balls? Yeah, you could pick all 3 from the rest. Is it possible that you pick 1? Yeah, 2, 3, same with Y. Okay, now how about joint? Well, what is the different possibilities? So let's write down now range of X comma Y together. Okay, what can be? Can you pick nothing? No red, no white, and only pick blue balls? Yeah, you can pick no red, no white. Can you pick exactly 1 red and no white? Yeah, you can do that. Can you pick no red and 1 white? Yes. You can pick 2 red and 0 white? Yes. You can pick 1 red and 1 white and 1 blue. And you can pick 0 red, 2 white, and 1 blue. All right. You can pick 2 red and 1 white. You can pick 1 red and 2 white. All right. And of course, you can pick all 3 of them red, no white, or you could pick no red and all 3 of them white. Okay, so let me actually make this parentheses better. So that is the range of the random variable X comma Y. All right, and they have shown the probability mass function in a very nice tabular fashion. I'll come to that in a second, but let's just pick any one of these numbers. All right, or 1 or 2 of these numbers. So let's say we're talking about P of 1 comma 1. What is P of 1 comma 1? This is the probability of X equals 1 comma Y equals 1. So that's the probability you pick 1 red and 1 white ball. How many ways can you do that? How many ways can you pick exactly 1 red and 1 white? That is 3 choose 1, the number of ways you can pick the red, times 4 choose 1, the number of ways you can pick the white. But don't forget, what does this mean? It means you've picked 1 red, 1 white, and white blue, and one blue, so you have to throw in the 5 choose 1. Totally, how many ways can you pick 3 balls from a total of 12? It is 12 choose 3. Okay, so that is P of 1, 1. All right, let's take another. What is P of 0, 0? This is the probability of picking 0 red, 0 white. So you have picked all 3 blue balls. So it is 5 choose 3. The number of ways you can pick the 3 blue balls divided by 12 choose 3. Okay. For example, what is P of 2, 1? That will be the number of ways you could pick 2 red. That's 3 choose 2 because there's 3 red and all. Times the number of ways you could pick 1 white ball. That's 4 choose 1. You can think of this as a multi-stage counting. And then that's all. You don't have to look at the number of ways you could pick blue. And then divide it by 12 choose 3. Okay, so it generalizes to all of them. You can take a look at that. Okay, for example, one more, okay, just for the sake of making sure you get this. What's P of 0, 2? The probability of picking 0 red balls and 2 white balls. So how many ways can you pick? So one way you can pick 0 red balls, just don't pick any. How many ways can you pick 2 white balls? It's 4 choose 2. And then you still have to pick a blue ball because this means you pick 2 white and 1 blue. So 5 choose 1 divided by 12 choose 3. All right. So that would be P of 0, 2. Okay. And if you look at all these numbers and calculate them, put them in a table. It's a table given to you on page 239. I'm just gonna write down some of it over here. Okay, just so that you get used to it. Let's go through it, actually, the whole thing. Okay, and this is I. The rows will stand for the red balls. 0, 1, 2, 3. Okay. J, the columns will stand for the white balls. All right, you'll have 0, 1, 2, 3. Okay. All right, and so what, for example, does this entry stand for? Or actually, let's do a different one. Okay, let's say what for example does the star entry stand for? It stands for P12. All right, what is that? That's the probability of picking 1 red ball and 2 white balls. All right, so these entries you can compute. This is 10 over 220. This is 40 over 220. This is 30 over 220. 4 over 220. Okay, and what about P of 1, 3? You cannot pick 1 red and 3 white because you're only picking 3 balls. So all of these where the sums of I and J are bigger than 3, they have to be 0. All right. Okay, now take a look at this row, the first row. Okay, so that is the probability of the first entry over here is the probability you pick 0 red and 0 white. The second entry over here is the probability of picking 0 red and 1 white. The third entry is 0 red and 2 white, and the fourth entry is 0 red and 3 white. If you add up all these 4 numbers, what are you going to get? You're going to get the probability of there being 0 red. Because 0 red can occur in 4 ways. With 0 white, 1 white, 2 whites, or 3 whites. All right? So summing each row gives you the probability x equals I. Okay, so sum gives you the probability of x equals 0, and this is 84 over 220. Over here, you'll get the probability x equals 1. If you add these 3, you have 9108 over 220. This is the probability x equals 2. That'll be 27 over 220. And there's only one. This is probability x equals 3. That is 1 over 220. Similarly with the columns. When you add up the columns, you're going to get the probabilities of yj. So this is row sums. Gives you probability of x equals I. So, and in the column sums, you'll have the probability of y equals j. Okay, so 40, 55, 56 over 220. Over here, 6112 over 220. And then over here, you have 48 over 220. And over here, you have 4 over 220. Okay. Okay, let's stop there for a second. Also ask yourself, what will the sum of the entries over here, 84 over 220, 108 over 220, 27 over 220, 1 over 220, what will the sum of these four numbers be? What are you doing? You're just adding up p of x equals 0, p of x equals 1, p of x equals 2, and p of x equals 3. That exhausts all the different possibilities that x can be. So this sum of these four entries in the last column should be 1. Similarly, the sum of these four entries in the last row should be 1. Okay, so those sums turn out to be 1. All right, so this tells you one thing, the relation between little p of x for the random variable x and little p sub y of y for the random variable y. Okay? All right. So that's an example that we had in the book. Just one little tweak that I wanted to talk about is, it's possible that you have, and this is just about actually about counting, not necessarily about this. Let's suppose you had 2 red. Sorry, let's go back to 4 white and 5 blue. Okay, then what's the range in that case of x comma y? So suppose this was the urn. Okay, then what's the range? Well, certainly, once again, you could have none. You could have 2 red, 0 white. You could have 1 red, 0 white. But you cannot have all 3 of them red because there's only 2 reds. And then you could have 2 red and 1 white. Or you could have 1 red and 2 white. Or you could have 0 red and 2 white. Or you could have 0 red and 3 white. Okay, just a small little play on what the numbers would be if you only had 2 reds. So just showing you that in that case, you just don't even need to go going from 0, 1 to 3. You can just have the first, only these 0, 1, and 2 rows. You don't even include the last row. Okay, so suppose urn look like this. Then you pick 3. Then the range of x comma y is given by this. Okay. So that's just showing you how you deal with joint mass functions and how you add up appropriate values to get the individual mass functions for x and y. All right. Okay. So I want you to take a look at example 1b in the book and 1c on your own. And if you have any questions, please, of course, if any of that doesn't make sense, please do email. Okay? And what we're going to move on to is a continuous case. All right. Now, remember in the continuous case, what did we have? We had f of x. What was that? If we wanted the probability of x being in A, you say f is the density of the random variable A. if the probability x equal in A is given by the integral over A of this density function. Okay, what was the density function satisfy? It was non-negative. The integral over the whole plane, not the whole plane, the whole line is 1. And for any set A, the probability x being in A is given by the integral of f over A. Okay, so just a small little thing. I've obviously not written everything over here. Okay, so in the continuous case, when we have more than one random variable, well, we have some extra stuff going on over here, and we say that the random variables, so x and y are continuous random variables on the real line, and we say that the random variables x and y are jointly continuous if there's a function on R2, okay? In the book they write define for all real x comma y, which is the same as saying function on R2, such that for any set C, which is a subset of R2, okay, the probability that x comma y as a point in R2 belongs to this set C is given by the double integral over the set C of this function f. And now it's a double integral. Okay, sorry, I didn't write the function f before. So the probability x comma y is in this set is given by the integral of that function over that set. Okay, so if you want to write it in a more rigorous way, you say x comma y equals c. All right, and herein, of course, now the tools of higher integrals that you've learned in Calc 3 will come into play over here. Okay, so for example, what if you wanted to ask what's the probability x is in some set A and y is in some set B? Then you can think of C as a Cartesian product of A cross B. Okay, if you've looked at Cartesian products of sets. If not, you can just take a look at this and say you have dy on the outside, then the limits of y are over the set B. The limits of x are over the set A. Oops. And you are integrating f of xy over the set C, which is A cross B, or this. All right. And now, once again, just like we did in the single variable case, looking at the relation of the CDF and PDF. So over here, let's take a look. What is f of A comma B? We know from before that's the probability x less than or equal to A comma y less than or equal to B. Well, then in that case, you can think of this as x belonging in the set negative infinity to A, comma y belonging in the set negative infinity to B. Okay, and think of it in that fashion. So what will that be? Integral from minus infinity to B for the y limits, integral from minus infinity to A for the x limits. You have to integrate the joint density like this. Okay? So that shows you how do you find the CDF using the PDF. Okay, how to find the cumulative distribution function using the probability density function. You'll have to do this double integral. All right, now just like we had in the single variable case, what did you have? You had capital F of A is the integral from minus infinity to A of little f of x dx, and we did the FTC, and we saw that that means f prime of A is little f of A. Okay, so that was a single variable case. In this case, what do we have? So let me just write this. F of AB is integral from, negative infinity to b, negative infinity to a, f of x comma y dx dy. So for all nice functions, you know that you can do the integral in either order, okay? And that's something too that you will see that you have to do. In some situations, you cannot find the integral of f of x, y in one order, and you'll have to do a switch of order and things, exactly all the kinds of things you have, many of the kinds of things you had seen when you were doing integrals in Calc 3. Okay, so here's a relation, not the both direction relation between cumulative distribution function and probability density function. This is how you get the joint CDF from the joint PDF. Okay, but what about the other way? What is the other relation between these? Well, if you take this capital F and differentiate it with respect to B and then differentiate it partially, see, because it's a function of multiple variables, we're doing partial derivatives. If you do this, what happens? Just like you had seen in Calc 3, differentiating partially with respect to B will give you what? So this will be DDA of DDB of the integral minus infinity to B, integral minus infinity to A, f of x comma y, dx dy. Okay, so first let's do what's in the box brackets. And what will that be? Oops, sorry. That'll be negative infinity to A, and you have to evaluate this at B. So it'll be f of x comma B dx. Okay. And then differentiate this with respect to A, and you will have f of AB. All right. So the relation between this other relation between the CDF and the PDF, you can get the probability density function from the joint cumulative distribution function by doing a double partial derivative. Okay, so these two boxed identities that I've written, one on the top of the page here, one on the bottom, they show you the relation between the two. Okay, and it's just like we had in the single variable case, but now we have two variables going on. All right, so I hope this makes sense to you. And what we have to do next, just like we did in this discrete case, let's try and find the relation between the probability density functions of the individual function, individual random variable x and y, along with the joint probability density function of x and y. Okay, so let f sub x comma y be the joint PDF of x and y. How does this relate to the PDFs of, or maybe I should write, okay, how does the joint PDF relate to the individual PDFs? All right, so let's take a look. Okay, so what is the PDF of the random variable x? Okay, suppose we want to know what the probability x in A is. Okay, so let's relate this first to the joint PDF. What is this? This means that the probability of x being in the set A and y is anything, right? Or in other words, you can say this is probability x is in A and y is between minus infinity and infinity, which is always the case because y is a random variable. It takes on some number. Okay, so Now, take a look. How do you find the probability x in A, y in B? You integrate dy over the set B, integrate dx over the set A and of the joint probability density function, and you'll have this. So let's just do that. So y goes from minus infinity to infinity, right? So these are the y limits. X ranges over elements of set A, okay, of the joint density, right? This is what you have. Okay. Well, what can you do? I mean, in the book, in fact, they don't even write it in this order. They write it in the other. But I wanted to address the fact that most functions we're looking at are nice, and you can rearrange the order of integration and first integrate with respect to y. Okay, the reason I wrote this in the first place is because we've always looked until now at dx on the inside. So why not just show you it's the same thing? You know, you can have dy on the inside or dx on the inside. Okay, so the probability x in A, for let A be any subset of the real line. Okay, the probability x in A is given by the integral over A of this guy. You see that? So what do you know? This, let's call it f sub x, okay? Because when you integrate out the y, what remains? It's an x. So I'm going to call it f sub x dx integral over A. So the probability x in A for any A subset of the real line, you have this. What does that tell you? That means that f sub x is the probability density function of A. Okay, so that's the relation f sub x. You have to integrate out the y from the joint density. Okay, and similarly, you can get the density of y by integrating out the x. Okay, so the relation between the individual probability density functions and the joint density function. Okay, all right, so that takes care of all the theory from 6.1. Okay, it's important that we look at examples together. So even though I know they're in the book, they're very nice examples, I'm going to go through the examples from the book. All right? Okay, so let's do examples. Okay, so first let's do example 1D. What does that tell you? The joint density of x and y is given by f of x comma y. Whoops. Sorry, I'm just trying to get rid of this. Okay. The joint density of x and y is given by f of x, y equals 2 e to the negative x, e to the negative 2y, when x is between 0 and infinity, and y is between 0, oops, and it is 0 otherwise. Okay, so just let's stop for a second and look at this. What is this telling you? The joint density of x and y is 0 outside of the first quadrant. That means that x comma y as a point doesn't land in the second, third, or fourth quadrant, right? Or you can also from that conclude that x is never negative, y is never negative, okay? Or it's positive with probability 1, y is positive with probability 1, okay? And what are they asking you to find? Find or compute probability that x is bigger than 1, y is less than 1. So that's the intersection. And B, they're asking to find the probability x is less than y. So now we're talking about the joint behavior of x and y. And lastly, find the probability that x is less than a, okay, for a general A. Okay, so I always like to draw a picture, all right? So for part A, you want the probability here. Let's draw the line. Oops. Little x equals 1. And let's draw the line little y equals 1. So you want the probability that y is bigger than 1, x is bigger than 1, y is less than 1. So you want the probability of landing in that set. Okay, I mean, in this situation, you don't need to draw the picture, but as a rule, I always draw a picture. It makes it much easier to understand what's going on. Okay, so what do we need to do? To find the probability that x comma y is in that set, we have to integrate over that set. So what is that set? Y goes from, what's the range for y? It's really negative infinity to 1, but the density is 0 outside of the first quadrant. So you can just go y going from 0 to 1. Okay, what's the range for x? X goes from 1 to infinity. Okay, and you integrate the okay, and you know that these are the x limits, these are the y limits. The region is a rectangle in R2. It's an infinite rectangle, and the function is a product of 2. So you remember when you did Calc 3, if you had a function f of x, y, which was g of x times h of y, and the region you're integrating over was a rectangle, then you can just separate the two integrals. Okay, so here's what we'll do. We'll separate one of the integrals, and we'll separate the x integral. Okay, this is just a little calculation trick from Calc 3. And the reason I put the 2 in there is because I'll need it because of the chain rule. Okay, so u equals negative 2y, du is minus 2 dy, and so the integral over here is minus e to the minus 2y, y going from 0 to 1. Okay, you can work that out. And over here you have limit b going to infinity, minus e to the minus x, x going from 1 to b. All right, and so you plug in 1, you plug in 0, and it ends up being 1 minus e to the minus 2. And you plug in 1, you plug in b, take a limit as b goes to infinity, and that will be 0. So this turns out to be 0 minus negative 1. So this turns out to be 1. Okay. No, actually, sorry, it's not 0. I just evaluated the limit as 0 to infinity instead of 1 to infinity. Okay, so this will be minus e to the limit as b goes to infinity of minus e to the minus b minus of minus e to the minus 1. Okay, And what will that be? 1 minus e to the negative 2. This one is 0, and this is just e to the negative 1. Okay? So this product, that will be the probability that x is bigger than 1 and e is less than 1. Okay? You can also verify when you take the joint density and integrate it over the whole plane, you should get 1. And of course, the joint density should be non-negative, just like you had in the single variable case. Over here, though, you have to consider the whole plane. All right, so that's the answer to part A. Now let's look at answer to part B. What's the probability x is less than y? Okay, so now here's where all the fun starts. Okay, so once again, draw a picture. Okay. And draw the line x equals y. All right. And where is x less than y? X will be less than y. It will be this region. Correct? Let me draw it with. In this dotted region, not including the line x equals y. So you have to integrate the joint density over that dotted region. How do we do that? Okay. Okay, I didn't even include anything else from anywhere else because the joint density is 0 outside of the first quadrant. Okay, so let's take a look. You can say that y can be anything, okay? So say y goes from 0 to infinity and fix a y. All right, if for a fixed y, what is the range of x? For a fixed y, x goes from 0 to, what's this limit? That is the line x equals y. So in terms of y, x goes from, for a fixed, any particular y. So for example, y equals 3. If you don't like to just call it y, pick a number, let y equals 3, y equals 18. Then you know that x will range from 0 to 18 for y equals 18. X will range from 0 to 3 for y equals 3. So for any particular y, x goes from 0 to y, and then you integrate the joint density. Okay, so let's do this integration. Integral 0 to infinity. I'm going to throw the y bits out and the constant. I cannot separate these integrals because the region's not rectangular. All right, so 0 to y e to the minus x dx. Okay, so integral 0 to infinity 2 e to the minus 2y. Okay, what is this? It'll be minus e to the minus x going from 0 to y dy. So that is integral 0 to infinity 2 e to the minus 2y. You plug in y, you plug in 0, and this will turn out to be 1 minus e to the negative y. Okay. All right, so now it's just the integral of one variable. And I'll let you fill in the gaps, and this turns out to be 1/3. Okay, this is just standard integration. All right, and lastly, part C, you're asked, what is the probability of x being less than a? Okay, well, what do you have? Let's write down, let's draw a line x equals a. And what is the region? The region that you need to integrate the joint density over is that. So what will that be? Y goes from, or x goes from 0 to a, you could have that be inside, that's fine too, of, if you want, let's just in fact write it like this. Okay, so probability x less than a is the integral 0 to a of the density of x, which we know is integral from minus infinity to infinity of the joint density. Okay, that is exactly this. All right, or you could do an integral over this R2 region. It's all the same. It's going to work out to all be the same. So what do you have? Integral 0 to a, and you have integral, sorry, I shouldn't write minus infinity. I should just write 0 because the density is 0 to the left of 0. And let's throw the e to the minus x out. You have 2 e to the minus 2y dy dx. Okay. And you can work it out. This inside integral will just turn out to be 1. Okay, you can check. Integral 0 to infinity 2 e to the minus 2y dy. This is 1. And then you have integral 0 to a e to the minus x dx. And that turns out to be 1 minus e to the minus a. Okay, so you have, in fact, that's also the CDF of the cumulative distribution function of the random variable x, because, you know, that's the same thing when you have continuous probability x less than or equal to a is the same as the probability x less than a. Okay. All right, so I hope that example made sense. Let's look at one more example. And that is example 1E from the book. Okay, and the reason I want to do this is because this has got to do with a circle. Okay, so I won't necessarily do all the detailed calculations over here. You can refer to the book for that. But I just generally do want to talk about this example, just at least an overview. So what this example says is, consider a circle of radius r, and suppose that a point within the circle is randomly chosen in such a manner that all regions within the circle of equal area are equally likely. So what does this remind you of? Uniform. And in fact, what this is a uniform random variable uniformly distributed on this circle of radius r. Okay, so you have a circle of radius r, and every subset is just as likely as another subset of the same area. Okay. If we let the center of the circle denote the origin and define x and y to be the coordinates of the points chosen. So if you have a point, that would be x comma y. Okay. Then since x comma y is equally likely to be near each point in the circle, it follows that the joint density function, okay, now because it is uniform on the circle, you have that the joint density of x and y will be some constant on the circle, or maybe I should say in the circle, and 0 otherwise. Okay, and this, and what they ask you to do is 1, find the value of c. 2, find the marginal density function of x and y. What do you mean by marginal density of x and y? It's just the density of x and y. The reason you're calling it marginal is because it's coming from a joint density of x and y. Okay, and part 3, find the probability that the random variable d, the distance from the origin, of the point is less than or equal to A. Okay, and part D, they found the expectation of D. Okay, so what is this D? D is the distance of the point from the origin, all right? That's a random variable D you've created from X and Y, all right? Okay, so solution. What do you know about joint densities? The density or joint density over the whole plane, they need to integrate to 1. So you know that the integral over the circle of the density what's the radius of the circle? The circle has radius r. This should be 1. Okay. So you know that the integral over circle of radius, I just put a little circle with a dot, r of c dx dy should be 1. The integral of a constant over a region is going to be, you have seen this before, this is just the constant times the area of circle of radius r. Okay, you know that equals this, and you need this to be equal to 1. Okay, so what does that tell you? C times pi capital R squared should be 1. That means C is 1 over pi R squared. Okay, so you see this is analogous to what you have for uniform random variable on an interval. Uniform AB, if you have X is uniform AB, then the density of X will be 1 over B minus A. That's 1 over length of interval on the interval, and it is 0 otherwise. You remember this? So just same over here. You have a random variable that's uniform on a certain region. On that region, the density is 1 over the area. And outside of that region, it is 0. Okay, now let's look at part B. Part B, you're asked to find the marginal densities. Okay, so we'll just do one. All right, so what do we want? We want f of x. Okay, so that's the density of the random variable x. What did we see? How do we get the density of the random variable x from the joint density? Well, what do you need to do? You have to integrate out the y. Okay, so let's just draw a picture. Okay, no matter where your x is, you integrate out the y. Okay, so what do you have? This, you know, is you have to just integrate it on this region inside the circle. Okay, so if you have a given x, if you fix a certain x, what is the range of y? Y will go from, for any particular x, y goes from negative square root r squared minus x squared to positive square root r squared minus x squared. Okay, and the density is f of xy. Okay, you see, you have that, suppose x is in this interval, x going from r to negative r. If x is between r and negative r, So pick any x, okay? So here we go. Let's pick the x. What is the range of y? Outside of that top limit to this limit, let me just pick a highlighted color. So outside of that y limit to that y limit, the joint density is 0. So you only have to integrate from this bottom to this top, okay? So, oops. Let's just pick that. What will this be? Okay, so 1 over pi r squared comes out. You're integrating 1 over this. Okay. All right, so this is just integral of 1 will just be top limit minus the bottom limit. So it'll be 2 square root capital R squared minus X squared over pi R squared. Okay, and we need to write this down properly because we have to take into account that X is between negative R and R. So you have to put it all together nicely. The probability density function of X will be 2 square root r squared minus little x squared over pi capital R squared if x is between r and negative r and 0 otherwise. Okay, so that's the marginal density of the random variable x, or the density of the random variable x. And by symmetry, because it's a circle, you have that the density for the random variable y, or as they have said, the marginal density of the random variable y, will be the same thing in terms of y. Okay? So that tells you what the densities of x and y are. Okay, part C. You want to find the probability that the distance d from the origin to the point is less than or equal to a. So you want the probability d is less than or equal to a. Okay, well, that's really not so hard to calculate. All right, well, take a look. What do you have? Well, you know that here's your circle of radius r, okay? And distance from the origin, suppose you have this. That is A. Then any point inside this circle of radius A will have D less than or equal to A, right? So this will be the probability of being inside this circle. Okay? And so what do? You have to integrate the density over that circle. Okay. So what do you have? You have to integrate over the circle x squared plus y squared less than or equal to a squared, the density okay, because that's the same thing. This is the probability that point x comma y is in circle of radius a. Okay, so that's what you have. And because it's uniform, it's just going to be just like you had for one variable. You had the length of the interval divided by the total length. Over here, you'll have the area of the circle divided by the total area. Okay, or you can factor out f of xy, which is 1 over pi r squared, and then you're integrating over x squared plus y squared less than or equal to a squared 1 dx dy. So that is just pi a squared over pi r squared. Okay, I'm sorry, I shouldn't have this line coming out like that. Okay, which is a squared over r squared. All right. We need to be a little bit more specific. And of course, you have, so the probability of D less than or equal to A. Well, you know this is in fact the CDF of the random variable D, which is the distance from the origin. This is A squared over R squared if A is between 0 and R. Okay? And it is 1 if A is bigger than or equal to R. Because what's the probability that the point that you pick is inside this dotted circle, which is outside of the circle of radius R? Well, that's 1. It's always going to be inside that dotted circle if the dotted circle contains the circle of radius R. Okay? All right. So to be complete, always make sure you include these extra parts where the CDF is 0 or the CDF is 1. Make sure you always do that. All right, and of course, now part D, they ask you to find the expectation of D. How do you find the expectation of D? You integrate over minus infinity to infinity the probability density function of D. Let's put A. Okay, well, what is the density? Well, this is the derivative of the CDF. So what will that be? That'll be 2A over R squared if A is between 0 and R. Okay, it's never negative. Okay, actually I should include that too. I forgot to include that. So in the previous page, right here, f sub d of a, the probability d less than or equal to a, it's going to be 0 if a is less than 0. I forgot to mention that just when I was telling you that. Don't forget to say that, sorry. And it's 1 if a is bigger than r, and between 0 and r, that's what you have, okay? So when you differentiate it, you have 2a over r squared when a is between 0 and r. Derivative of 0 is 0. Derivative of 1 is 0. So you have this being 0 outside of that interval. So you just write OW, okay? Okay, so that is the density of the random variable D. Okay, so what is the expectation of D? That will be the integral from minus infinity to infinity of f sub d of a dA. Well, this density is 0 outside of 0 to r, so you just integrate from 0 to r. 2a over r squared, I'm sorry, a times this. Oh, I forgot to put the a. A times this, dA. Expectation of a random variable is x is integral of x times f of x. Okay, so expectation of d is a times f of a for the random variable d. Okay, and now you just do the integration. So 2 over r squared stays. Integral of a squared is a cubed over 3. A goes from 0 to r. And the reason I wrote this a goes from 0 to r, just to make sure you remember, you know which variable you're substituting. Okay, so you have 2/3. Okay, you have r cubed. Oops. Minus 0 over r squared, and that gives you 2/3 r. So the expected distance from the origin is 2/3 r. It's not 1/2 r. Why? Because it's not the distance from the origin, that's not uniform. All right. So that's the end of example 1E. All right, and just one last bit. I just will talk about 1F and just mention one more thing. Okay, the joint density of random variables x and y. Joint density is e to the minus x plus y when x is between 0 and infinity and y is between 0 and infinity. So this random variable is never negative, or negative with probability 0 and 0 otherwise. Okay, and they ask you find the density of the random variable x over y. Okay, so that's what you want to find out. What is the density of the random variable x over y? Okay, now x comma y, that's a point in the plane. What you're asked about is x over y. That's just a number. So now, given the behavior of the random variable x and y, or given the behavior of x comma y, you want to find out what the behavior of this single random variable x over y is. That's a number, that's a real number. It's not a point in R2. X over y belongs to R. Okay, so what do? Just like you did when you had functions of random variables in chapter 5. What you have over here is a function of random variable x and y. To find the density of a function of random variable, you always go via the CDF. Okay, so first find the CDF of x over y. Okay, so let's look at that. F sub x over y of a. Okay, well, take a look at x over y. X is always non-negative, y is always, or x is always positive, y is always positive. So you know this will be 0 if a is less than or equal to 0. In fact, it's never even 0, right? Anyway, it's continuous, so doesn't matter where you throw in a equals 0, but I'm just showing you that x is always positive, y is always positive, and so x over y, because you know the joint density is non-zero in the first quadrant, so you know x over y will never be negative. Okay? All right. And beyond that, let's actually try and find out what the calculations say. X over y less than or equal to a. Okay, that's just the definition. Okay, so let's work on that. You want the probability x over y less than or equal to a. That is the probability of x less than or equal to ay, or the probability of 1 over ax less than or equal to y, whichever way you want to write it, that's fine. Or you can say this is probability of x comma y being in, what do we have? Let's draw the line. Or here, let's, y equals 1 over ax. Okay, and y is bigger than 1 over ax. Let me just call this region R sub a. Okay, this is the same as the probability x comma y is in this region R sub a, right? And so what do you have to do? You have to integrate the joint density of x and y over that region. All right, so what do we have? Y goes from 0 to infinity. Okay, let's do that. Y goes from 0 to infinity. Okay, for each fixed y, what is the range of x? X starts at 0 on the left. And what is this? What is this x value in terms of y? Y equals 1 over ax. So the limit when you're going along over here, let me take a yellow marker. On this, you're going along. When do you have to stop? In terms of y, it depends on the y. The further high up you are, the further away you'll go. Lower you are, the quicker you stop. And when do you stop? You stop when x is a times y. Okay. Oops, sorry. All right, and you put in the joint density. These are the x limits, and these are the y limits. dx dy. Okay. So integral 0 to infinity, integral 0 to ay, e to the minus x plus y, dx dy. All right. You cannot separate out the integrals because the region is triangular. So integral 0 to infinity, integral 0 to ay, e to the minus x, e to the minus y, dx dy. Okay. Okay, so you do that integral. It's a dx integral. Okay, so it's minus e to the minus x going from 0 to ay dy. Okay, so it'll be integral 0 to infinity e to the minus y. 1 minus e to the minus ay. Okay, dy. Okay, now you open this parentheses up, do the integral, and this turns out to be 1 minus 1 over a plus 1. Okay, so what have we done? So far, all we have done is found the cumulative distribution function for x over y. Okay, so f sub x over y of a, I'm just writing x over y like this over here, is equal to 0 if a is less than or equal to 0, and 1 minus 1 over a plus 1 if a is bigger than 0. Okay, and then you differentiate it, and you know that the density will be differentiating a plus 1 to the negative 1, negative a plus 1 to the negative 2. So it is 1 over a plus 1 whole squared if a is positive and 0 otherwise. Okay, so that is the density for the random variable x over y. Okay, I just thought it's important that you saw some examples done, so I did all of these. And lastly, I just wanted to mention one quick thing. Just like we did this for two variables, you had two variables, so you have f of x, f of a comma b, that's the probability x less than or equal to a, y less than or equal to b. So suppose you have random variables capital X1, capital X2, all the way till capital Xn, then you could do things like you could have a joint CDF of all these n random variables, f sub a1, a2, an, and that's the probability x1 less than or equal to a1 and x2 less than or equal to a2, and xn less than or equal to an. Okay, you could talk about that. And you could have a joint PDF, for example, if it's continuous, and you will have a set C in Rn. You can integrate over C in Rn this joint PDF to get the probability that that point as a point in Rn is in this set C in Rn. Okay, so this is just generalizing what we have for two random variables x comma y to more of them. Okay, so I think that's good for now. I want you to look up the example, the multinomial distribution example from the book on page 246 of the 10th edition. Okay, so I will stop right here, and I hope that this made sense. I want you to remember the key things. The main things over here are you have the joint CDF. In case of discrete, you have the joint probability mass function. In the continuous case, you have the joint probability density function. What is the relation for each one of these to the individual mass functions and the individual density functions, which we're calling the marginal. And what's the relation between the joint CDF and the joint PDFs, and how do you use the probability density functions to find probabilities. And otherwise, it's very similar to what you did in one variable. Of course, the integration, you have to be worried about a region in R2. So you need to be more careful about the calculus part of it. Okay? All right. Don't forget, please email if you have any questions. Okay. Thank you guys for listening.